Welcome to this quick presentation on the centripetal acceleration and centripetal force. The approach I will take in here is going to be mainly calc-based, but at some point I will touch bases with algebra-based, basically approach and how to introduce these ideas. Anyway, before I start doing that, let's review some of the concepts that we must have seen from before, namely the fact that let me go back into the idea that the vector position R describes the position of a particle on a two-dimensional, basically, space, and it's given by its x and y coordinates in such a way that that vector has the magnitude is given by the Pythagorean theorem. Basically, according to this graph, you clearly see that the x component squared plus the y component squared is just this length squared, and the direction is given by the ratio of the y component over the x component, namely that the ratio is a tangent of this direction. In the case of a circular motion, it's described when this particle moves around at a constant radius. The radius does not change. At a constant distance from a central point, which we're going to call the center of rotation. That's the radius actually, r. So this magnitude is fixed at all times. Furthermore, if we're going to assume that somehow this motion is uniform in the sense that the angle with which this is changing changes at constant rate, and that rate is omega, that is what we call the angular frequency or the angular velocity. So basically, this approach will give me the following description. So basically what we have in this case, the x from the previous slide, is equal to just basically the r itself, which is fixed number times cosine of phi, and phi is omega t. So that's basically the x component, similarly the y component. And from here, the vector r itself is no more than actually a constant number r, because I have to pull the r from both of them, from both of these two terms, and I will be left with cosine omega t in the I hat direction and sine of omega t in the j hat direction. Interestingly enough, this is actually a vector of unit length, the one in between parentheses, because of the fact that its magnitude is the square root of x squared plus y squared, then its x is cosine of omega t and its y is sine of omega t, and square root of sine squared cosine squared plus cosine squared is just 1. So this is a unit vector, and it's actually pointing in the radial direction, actually from wherever the center of rotation to the point where the object is, because actually that direction is the same as that of the position of the particle. So this is the radial unit vector r hat. Now, this motion again is uniform, and it repeats itself after each period t, which is just equal to 2 pi divided by omega. All I have to do is impose that this number equals to 2 pi, and from there I'm going to put that condition. So this is a period of revolution around the center of rotation. If I'm interested in the velocity is the derivative of the vector position with respect to time, and r is constant, so the only thing that changes in this case is the r hat. So I use the chain rule and take the derivative of cosine omega t with respect to t. I pull an omega in both two terms, and I will flip the sign of the cosine. That's a property of the derivative of the cosine, and keep the sign for the sine function when I take its derivative and change it to a cosine. This is basically the derivative of that vector. Note in here, r is constant, that is circular motion. Omega is constant, that's a uniform circular motion. So this is the vector of constant magnitude, because the magnitude of this number, no matter what t is always 1, because square root of negative sine squared, so the negative squared is going to be a positive, plus cosine squared is positive. So the square root of sin squared plus cos squared is going to be 1 no matter what t is. So therefore, actually, this thing also is a unit vector, and that unit vector happens to be perpendicular to the original vector. This is a cos, that's a cos, this is a sin, that's a sin. The only difference between these two vectors is that pi over 2. Using a trig identity in here, namely cos of alpha plus beta is cos minus sin, and sine of alpha plus beta is sine of alpha cos beta plus cos sin, basically, you flip the order. So using that identity in here, we can see that these two vectors are related. Both of them have the same length, which is 1, but they make a 90-degree angle, namely they are perpendicular to one another. As a matter of fact, this points in the direction with which phi is pointing, because phi goes from the x-axis toward the position, same thing with this vector. So this is what we call the azimuthal unit vector phi naught. And the velocity then can be written as basically omega r times I hat times, times phi hat. And if the magnitude of that b also is constant, and that's a very important relationship that we're going to need. Now, if I'm interested in the acceleration, all I have to do is take the derivative of this derivative, and r omega is constant, and all I have to do is just put another omega from the chain rule, so I'm going to end up with omega squared in here, and the derivative of a negative sign is actually going to be a negative cosine. The derivative of a positive cosine is going to be a negative sign. So I'm back to the cos sin, except I have a negative sign, which I'm going to pull out, and all of a sudden this acceleration actually points toward the center of rotation. So this is what we call a centripetal acceleration. So because it's pointing all the time toward the center of the rotation, its magnitude is r omega squared. And r omega squared, if I use this expression here that relates to omega and b, I can write it as b squared over r. So that is the magnitude of this acceleration, but it's always pointing toward the center, away from r hat. Whichever r hat is pointing, this is pointing 180 degrees away from that. So this is how it looks basically graphically. All I have in here is a position of a particle described again by this r hat, which is the radial unit vector, and the phi hat, which is the azimuthal or the angular basically direction, the angle direction, phi hat. Both of them are unit vectors. But this coordinate system has a peculiar property in the sense that it's always moving. So r hat is changing with time, and so is phi hat. And this reference frame is actually not stationary, but it's in motion all the time. And from the vantage point of a person looking at it from the stationary reference frame, namely given by this Cartesian coordinate system x and y, the particle itself is moving. So that reference frame is not aware of r hat and phi hat, but aware only with I hat and j hat. So from the stationary perspective, basically all I'm going to do is just do sum of the forces equals to ma, since I know the direction of the acceleration. So at least sum of the forces in the radial direction, when I project that expression in the radial direction, is going to be exactly given by that value, negative the mass times the acceleration, provided I took the radial direction pointing outward from the center of rotation. So from here, there is no problem. But from the vantage point of the person moving with the reference frame, he is stationary or she is stationary. They are not moving at all. But they are experience this force in here, which they think exists. In order for them to apply F equals to ma, so they have to be stationary. And in order to account for the fact that they needed to be restrained in order to fly on the opposite direction, they introduced this fictitious force to account for that. So it's not a real force, but for them to make the laws of mechanics work, in a sense, put F equals to ma. But we know actually Newton's laws should not really be equivalent between these two reference frames, because actually this is a non-inertial reference frame. The two reference frames, they're not moving with basically constant velocity with respect to one another, because this velocity actually is changing in direction. So v is v1 initially, then v2, and that's the difference between them. That is actually a change in velocity, and hence that's actually what gives rise to this acceleration. So this is basically how this looks like. Now, if I were to do this actually with students who were not really doing a lot of calculus, or even for the calculus-based students, it's a good idea to do something visuals. The visual will always help, and even for a calc-based course, it's very important that we see that too. So what I have in here, I have an activity with GeoGebra. I have basically a particle that is restrained to move in this path, which is clearly a circular path of a given radius. I can change the radius, make it smaller or even smaller than that. I can also change the frequency with which this moves. Right now it's at a low value. Right now I change it to a super high value. That means it's going to have very high velocity as it moves around. Or I can have it medium value or even a lower value depending on how I choose this thing in here. Again, this is a lower value, so it's going to move around. If I start it, it's going to move slow. But if I increase the frequency, I shouldn't do it while it's that derivative when we took it. We took it in the case when omega was constant. But right now I'm going to change the value of omega to see that actually two things happen. First of all, this is going to move faster. The value of v increases, and so is the acceleration. In all of the cases, the acceleration is always pointing toward the center of the rotation. That is what we call the centripetal acceleration. Sometimes it's called the normal acceleration because it's perpendicular to the path of the particle as it's moving around its center. So that's basically a visual to help us understand this concept of centripetal acceleration, which is pointing toward the center. From our vantage point, we can always apply F equals to ma and know that the forces, when they are in the radial direction, they must be equal to the mass times that acceleration. From the vantage point of a person moving with the reference frame, they have to invent a force to make things make sense for them. Otherwise, this is a problem. So again, I'm going to take an example in here, and hopefully we can illustrate this idea in here. So the example that I have in here is of a pendulum, basically conical pendulum to be specific. What I have in here, I have a string of a length L attached to a mass, and I'm forcing it to spin at an angle theta. The angle theta is fixed. So I'm interested in trying to find the period t with which this goes around if I'm going to use this as a clock. Furthermore, I need to know the tension, because is my string going to support that force or not? All I have to do is, there are two forces in here, the gravity and also the tension in the string. All I have to do is add these two forces and enforce them from my vantage point to be equal to the mass times acceleration. And there are two directions in here of interest. There is the vertical direction, which gives me that force, again, in the chord itself, the tension in the chord, which is mg over cosine theta. And if in the horizontal direction, again, I have the sum of the forces. Mg has no component. The only component that is left is this force times sine of theta equals to mass times acceleration. And I solve for this problem, basically, and knowing that omega is equal to 2 pi over t, and using geometry in here to help me to find what this radius of curvature is, the radius of this circular path is, which is just given by L times sine theta. Solve this equation basically algebraically, and I find the period to be 2 pi times square root of L cos theta over g. Interestingly enough, let me do this demo quickly in here. Interestingly enough, if I were to basically change theta, I might encounter some problems. So that's I have about 30 centimeters basically of string in here. Is it clear? Yes. No, actually this is more. Let me shorten it a little bit. I have a mass which is slightly less than actually 100 grams, and that's what the number that I'm going for in there. And the angle theta is roughly about this angle. So I try to maintain it around that angle, and the period of oscillation there should be about 1 meter basically. 1 second. So this is taking about 1 second to go around and around. If I were to increase the angle, basically making it spin faster and faster, I have to be very careful in here, because the tension can, I'm sorry, but the tension in here can be very high. If I reach, for example, an angle of 89.9, I did not reach it earlier, by the way. I probably got around 85, which is really about 10 or 15 newtons, that's all. It's not really a big deal. But when you reach very high angle, namely very close from 90 degrees, remember the cosine theta in here will blow up, will go to infinity, and the tension in here becomes so huge that this string probably is not going to be able to support that force in here. And in this case, it reached 5,600 newtons, or actually more than that, and the speed will reach almost 300 miles per hour. This is going to be super fast. I mean, this is going to be incredibly fast at that incredible speed. So you have to be very careful when we do this one in the lab, because we don't want to go to too high velocities, otherwise we'll have disaster before our hands. Another typical example when we do this idea is actually when we take a curve. How fast can we go around the curve before we start sliding? So there are two solutions to the problem. Either you put a lot of friction on the road, this is what I'm going to do right now, or you actually tilt the road a little bit, banking the curves, basically. That could also solve the problem, or doing both of them, actually. That's the third option. So the problem in here is to find the speed limit with which a car can take this turn without sliding, and there's just the friction itself. So if we do that, then in this case, I'm treating the car as a point particle, and the sum of the forces, there are only three forces in here. There is the force of gravity pointing down, there is the force of the normal force pointing upward, and there is the force of friction, which is pointing toward the center of the curvature, because the car, if it slides, it's going to slide this way, so the friction will prevent it by applying a force opposite to the direction of motion, or the intended direction of motion. We don't want it to slide. If we slide, we have a problem. So basically, at this point, it's static friction, not kinetic friction. So apply the sum of the forces in the vertical direction, that gives me the normal. Apply the forces in the radial direction, that gives me, again, force equals to mass times acceleration. And impose a condition that the car will start sliding One, that condition is met, mu s times n is equal to, basically exceeded when that force exceeds that value. So as long as the force of friction is less than that, we're in good shape. So from here, we solve for that and basically sub the value of the acceleration in equation 2, and we get the velocity. The maximum velocity we can take this curve, if we don't bank the road, it has to be square root of the coefficient of static friction times g times the radius of curvature in here. As an example, I'm taking in here r to be 60 meters, mu s to be 0.7, and we found the speed limit to be about 45 miles per hour. Obviously, this is too high of a value. You have to really have 60 meters, is almost a half football field, or at least slightly more than that. So, or half soccer field. So you have to be careful with this one in here. If it's a sharp turn, this speed limit will be lower too. That's why you have to tilt it a little bit or take the curve slowly. So this is in a nutshell basically an introduction to the centripetal acceleration, both numerically in here. Like I said, for a algebra base, since we don't do derivatives and things like that, we give the formulas, for example, for medical students, and we deal with that, and we do a lot of problems. These problems don't require actually don't require calculus at all to do, so they are actually algebra. All I have to do is do my free body diagram. Once I do my free body diagram and I'm in good shape, and solve algebraic equations and put in the numbers, and we have to find them. So these are 2-3 steps basically, although this example might be a little bit more than that, but that's basically what these things are. So we should be able to understand. A visual, actually, I think GeoGebra is still going on behind the scene. A visual is very much helpful in here to understand this motion, and actually it's very helpful also even for calc-based students. I would say that too, because sometimes you talk to them and they tell you, hey, if you give me the equation, I can do the physics, but that's not true. I mean, physics is about all setting up the problem. If you don't understand the problem, you're not going to be able to set it up. It's not about solving equations. That's not really what physics is all about. It's understanding what's going on in this case. So this is an introduction to the centripetal acceleration and the centripetal force associated with it, as seen from two basically reference frames, from the stationary reference frame, which is just like mass times acceleration. That's all there is to it. And from a person moving with the frame, trying to basically mimic inertial frames, so he or she must introduce a fictitious force to account for that. Thank you.